But yeah, I'd like to start with a recap of really of everything I said last time. So let me get started. Right, the first theorem we had was this existence of sort of mini-versal presentations, or in other words, like the minimal smooth presentations of an algebraic stack, where namely that you can always find given these hypotheses that of an Noetherian algebraic stack, and I'm taking a finite type point and a smooth stabilizer group, then I can find a smooth presentation u over x of minimal, whose relative dimension is equal to the dimension of the stabilizer. So in particular, if the stabilizer is finite, then you get an Natal cover. Right, and what we showed was that this was a mini-versal deformation, so that we showed that that the induced map on tangent spaces at U is an isomorphism. That was the sort of our definition of mini-versal presentation. And then we also then could sort of use this to show that if X is a finite type over a field and the stack is smooth at X, then we can compute the dimension of the tangent, the dimension of the stack, at least locally, as the dimension of the tangent space of this vector space minus the dimension of the stabilizer. Yep, and right, and like our most important application of this theorem was in the case of Deligne Mumford stacks, and we're able to give this equivalent characterization of Deligne Mumford stacks. So if you have an arbitrary Noetherian, if you have a Noetherian algebraic stack, you can check its Deligne Mumford by just showing that all of the points have finite and reduced stabilizer groups. And the upshot of this is that it's much easier to show that certain moduli stacks are just algebraic. And then you can then apply this corollary to get that as Deligne Mumford. And so we use this to get that MG is Deligne Mumford. Right, and then we discussed two additional notions, both that had their own value of criterion. We talked about smoothness, and we talked about properness. Smoothness was the following lifting criterion, so a morphism of algebraic stacks is smooth if and only if for every such diagram here there exists a lifting, right? And then like Atalness was there's a unique lifting, on ramified there is at most one lifting, but we're mostly concerned about smoothness. And I guess often sort of the existence of such a lifting translates into a very explicit question. Often there's an obstruction to the existence there's an obstruction to the existence of this lift, which is measured by an element, which is like the obstruction itself is an element of a cohomology group. Right, and maybe I shouldn't say often, maybe I should say always, because, there's always, in a high degree of generality, you always have a cotangent complex, and that is exactly measuring, or you can use that to give an obstruction to the existence of this lifting. It's an X class of this cotangent complex, but that's often very abstract. And for moduli problems, you can often, the cohomology group is usually explicit, and you can compute it, and you can then use this to verify smoothness. And that's what we did last time, right? For MG, like if you have One is that it suffices to check on local rings. So if you have a diagram like this for Mg, say over spec Z, then if these are local, say local Artinian, then you can restrict to the residue field. And then this is a curve, you know, over a field. And then the existence of an error like this, what we showed, is determined by a cohomology class, an obstruction in H2 of C of the tangent bundle. As long as, okay, yeah, as long as you assume that this is a small extension. Meaning that the kernel is actually just the field K itself. Otherwise, you need to just tensor with the ideal sheaf defining this infinitesimal extension of Artin rings. But the point was that we could, you know, this is quite explicit in the case of curves, that because curves are dimension 1, this vanishes. So the obstruction always vanishes, and there exists a lifting. So this we use to conclude that Mg is smooth. All right, and the last topic we discussed was properness, and I raced through that. So I wanted to take some time and explain both separatedness and properness for algebraic stacks. So the definitions are sort of like, so the definition of a morphism of algebraic stacks being separated is that the diagonal is proper. Right, that's the first definition. And then properness is that the morphism is finite type, universally closed, and separated. Right, these are the definitions, and you might be worried that they're sort of circular because separatedness is defined in terms of properness, properness is defined in terms of separatedness. And I was trying to be careful last time, but I went quickly. But the point is that sort of separatedness is defined in terms of properties of the diagonal. And you sort of bootstrap earlier notions. So the diagonal is representable. And so you first define properness for morphisms of algebraic spaces, and then so on. Hopefully that's okay now. But yeah, it does require some work to precisely define these notions. But in the case of schemes, we recover the usual notion. If X is a scheme, then remember that always implies that the diagonal is a locally closed immersion. And then it being separated is equivalent to being a closed immersion, or that the image under the diagonal is closed. So X separated is equivalent to the diagonal being a closed map or closed immersion. And it's also the same as saying it's finite or even proper, because the diagonal in this case is a monomorphism. And and then going to the world of stacks, maybe a first example of something that should be separated is BG for a finite group. BG, if G is finite, and BG is separated because if you look at the diagonal and you base change, you get G itself, right? And this is an italic cover, and this map is finite. Right, and actually for a similar reason, you see that the classifying stack of an abelian variety or an elliptic curve is proper. Well, in particular separated. But let me give you another sort of example of sort of a new type of non-separatedness for Deligne Mumford stacks even. So let's consider the action of Z2 on the non-separated affine line. Let's call it U, which is equal to the affine line with two origins. And let's take the action which fixes everything except for the two origins which it swaps. Except swaps the origins. And then I'm going to take this quotient u mod z2. And my picture is that, well, basically it looks like the affine line. And because everything outside the origin is fixed, there's sort of a generic Z2 stabilizer, except at the origin, there's a Z2 stabilizer. And then here, there's a trivial stabilizer. So it kind of looks like A1, but the stabilizer group jumps down at the origin. And then if you translate what that means in terms of separatedness, so we have, let's call this stack X. And so we certainly have a cover U to X. But U is the non-separated affine line, so I could just, find an A1, just choose one of the copies of A1 over it. And let's think about what the stabilizer group scheme of this map F is. What is the automorphism group scheme of F, over A1? Well, generically, this is Z2 stabilizer, and over the origin, there's just, it's fixed. So it looks like the group scheme looks like you have, so here's my A1. And then I have the identity component, and then the -1 part, except I remove, the -1 over the origin. And it's clearly this is not finite. And separatedness is the condition that the diagonal is proper, or equivalently, all of the automorphism group schemes of like points of X are proper over the base. And maybe I should point out, in this stack is this gives me a group scheme G over A1, and our stack X is equivalent to the classifying stack over A1 of this group scheme. So so separatedness for Deligne Mumford stacks, it ensures that the stabilizer groups don't jump down in cardinality as you degenerate. And maybe another example is that BGM itself is not separated. And I mean, the reason is that if you take the diagonal and base change, you get back GM. And this is like an affine group scheme, but it's not proper. And so you see, like, groups like GM or GLN, their classifying stacks are never going to be separated. And a fact here is that, if you have an algebraic stack with affine diagonal, which is a rather weak condition, then X is separated if and only if the diagonal is actually finite. Right, and the reason this is true is that, if X is separate, if X has affine diagonal, the diagonal is affine. If X is separated, then the diagonal is proper, and proper plus affine equals finite. And so algebraic stacks with affine diagonal and positive dimensional stabilizer groups can never be separated. So maybe this is an important point here. So algebraic stacks with affine diagonal and positive dimensional stabilizers are never separated. And so examples that are A1 mod GM, or like in the context of moduli, is like the stack of vector bundles over a curve. These are not separated. MG, we will show MG is separated. We don't know that yet as a course. Like later, we'll show MG is separated, even proper. Right, and that gets us to now. Yeah, now I want to state the value of criterion, which I had just I mentioned last time. So, like with schemes, there's a value of criterion for either of these notions: universally closed, proper, or separated. But maybe let's just focus on the proper condition, which is 3. So we tested on valuation rings, or in the Noetherian setting, we tested on discrete valuation rings. And properness is saying every such diagram like this, after possibly an extension of the valuation rings, you can find a lift. And moreover, given any such diagram, any 2 lifts are isomorphic. Right, so it works just like the value criterion for schemes, but there is the one additional subtlety that you have to allow extensions. And right, and this is equivalent it turns out for schemes, if you have an extension, if you have a lifting after an extension, you can use that to actually produce an extension over the original DVR. But that's properness. And it's this value of criterion that we're going to use to show that MG is proper. So later, we'll show MG is proper what we need to show if you translate this condition is that, you start with, you need to show that for all DVRs are that when you start with maybe a curve, let's call it C star over the fraction field of that DVR, and you want to know if you can extend it to here, that given such a diagram, well, that you can at least find after an extension, spec R prime, spec K prime. So there exists this such that when you restrict this curve to K prime, there exists an extension C, say over R prime, that extends this curve, and it's unique. So the picture is, well, we'll get into this later, but you should have this picture in your head where, your spec R looks like a one-dimensional base, and you have a central point of it, and you're starting with, a family of curves, except you don't know what goes in here, and you need to show that after possibly extending the base curve, that you can fill it in with maybe a singular fiber. Right. And maybe the other example I would want to show, maybe I should just return, let me just say, like we saw in the last page that BGM was not separated. And you can also see this via the value of criterion. Let's just do this example again. BGM. If you translate the value of criterion for separatedness, well, we need to look at diagrams like this. Maps to BGM correspond to GM torsors, or equivalently to line bundles. And this is a field. All line bundles are trivial. So this is, the trivial GM torsor. And R is a local ring, so any extension here would also be trivial. So let's suppose we have 2 different extensions, both given, but they're both the trivial one, the trivial GM torsor. But remember, part of the data of these commutative diagrams are also these two isomorphisms. So in this case, what that means is you're specifying an isomorphism. So you're given an isom of the commutativity of this gives you an isomorphism of the two trivial GM, the two trivial. So let's call these maps H1 and H2. We have an isomorphism over the restriction. But this is the data of just an element of GM of K. And the value criterion for separating this says, will tell you that is asking whether you can extend this isomorphism over spec R. And so the point here is that this does not necessarily extend to GM over R. I mean, for instance, you could just take, if pi is a uniformizing parameter of R, you could just take the element like 1 over pi inside here as your isomorphism of the trivial families over spec K that does not extend to an isomorphism over spec R. So I'm partly saying this to emphasize, that you can see that BGM is not separated through the value criterion, but you need to think, you sort of, the two commutativity in these diagrams shows up in these conditions. Right, okay, I think that's everything I wanted to say in terms of recapping. So it's a good place to pause for questions.
So is it obvious that every principal bundle over spec R is trivial?
Oh, so the question was, is it obvious that a principal bundle over spec R is trivial? And in this case, it is, because we're taking principal GM torsors, and a GM torsor corresponds to a line bundle. And over a local ring like spec R, all line bundles are trivial.
Okay, thank you.
Other questions?
I guess MG should be MG bar near the top.
Oh yeah, thanks. Yeah. Oh, all right. So we have two goals in mind for today. One is discussing quasi-coherent sheaves, and the other is this local structure of Deligne Mumford stacks. So we'll start with quasi-coherent sheaves. And I should say, actually for a lot of this chapter and for a lot of this course, we actually won't need that much about quasi-coherent sheaves until the very, very end when we talk about projectivity. We'll need to construct ample line bundles, and we'll use sheaf theory. But in fact, even for the proof of the Kiyomori theorem of the existence of coarse moduli spaces, the only sheaf we're going to use is the structure sheaf. But for Deligne Mumford stacks, the theory of quasi-coherent sheaves, it works just like schemes. So I just want to give a quick summary and just emphasize that it does work exactly like schemes. So we'll start. And there is subtlety of extending this to algebraic stacks, which I won't address. So we're just gonna define quasi-coherent sheaves on Deligne Mumford stacks. And so we define the small étale site of a Deligne Mumford stack just as we define it for schemes. So the small étale site is just the category of schemes that are étale over the stack. So an object here is just a morphism from U to X, which is étale, and where this is a scheme. And then coverings are, and morphisms are morphisms over the stack X, so two commutative diagrams. A covering is just a sequence of Étale maps like this, where these maps, again, these are maps over X. And so these are Étale maps such that the disjoint union surjects. Okay. And so this gives us the notion of sheaves. And this gives us, sheaves on X Étale. Like we can discuss sheaves on any site. And we can take the category, let's write this, sheaves on X. This is the category of sheaves. And so it just maybe to spell it out, if you have a sheaf here, what that means is for every, so this part of the data here is that for all schemes U and Étale maps to X, where here U is a scheme, you have an associated, you have a set of sections defined over that element.
This might be a silly question, but
sure.
Since your category is really only defined in terms of schemes, does this site remember what it means to cover your stack X, or does that even make sense? Like, does it remember like the presentation as some sort of cover, or is that not?
No, it doesn't. No.
Okay.
Yeah, no, you have. Yeah, it's not. Well, it does not remember like a particular presentation. If you want, you could define a sheaf by just defining it on a particular presentation. But in some sense, in this definition, we're defining it on all, not all, on all presentations, and even all Étale maps.
But I guess what I'm asking is, does the site know objects that cover the stack, or?
Well, the site does, because we have coverings as well. I guess tautological.
Oh, I guess yeah. I mean, okay. I'll have to think about it.
So, for instance, can you recover the DM stack from its small Étale site in some way?
Okay, that's an advanced question. I guess no. I'd have to think about this. I mean, that's an advanced question. We won't really need this, but I guess no, right?
Well, I'm happy I managed to ask an advanced question. It's fine if we can answer it now.
Yeah, the small Étale site of like even of a scheme and like a nilpotent thickening of that scheme should be the same. Or I hope I'm not saying something wrong. Right. Oh, okay. So we have sheaves, and so by definition, so you have sections over every Étale morphism from a scheme, and you can actually extend this. In fact, can extend to Étale maps like U to X from DM stacks, where the idea is you simply choose a presentation. So this is an Étale presentation, and then you take, the corresponding groupoid R, which is, the fiber product of U and U over the stack U. And then you just define, you can define sections over this Étale map by just taking, by taking the thing that forces it to be sort of a sheaf. You take the equalizer of sections over U under the two maps to sections over R. And what this actually allows you, so if you wanted, you could use this construction then to enlarge your site where the objects are all the Deligne Mumford stacks Étale over this. And then the way I've defined it here would be a basis for that. site, our basis for that topology. But the main reason I'm doing this here is that, in particular, we can now define global sections. That we take the global sections of a sheaf is just the sections of F under the identity map. Great. So we have global sections, and and then we have a lot of similar properties to sheaves of schemes. Maybe I'll just say it this way: there exists adjoint functors. Okay. For any map X to Y of Deligne Mumford stacks, you have adjoint functors that you could take it. You can push forward and you can also take the pre-image. And this is defined just like with schemes, like the push forward. Suppose I have an F inside here. Let me do it in the color. F, then F push forward of F is a sheaf on Y, which to any étal cover, to any object, you just take F over the fiber product. Where this is a DM stack, so we're using this extension of sections. And the inverse image is always trickier to define, but it's in this case, it's just like with schemes. So if I wanted to take the inverse image of G evaluated on U to X, where this is étal, I just take the limit over all sections of all refinements. Let's say V to Y, where this limit is over all diagrams U to V, X to Y, where everything is étal.
Wait, I don't think you can define global sections that way, because the sheaf is only defined on schemes, right? Maps from schemes.
Yes.
Oh,
you mean way up here?
Yeah.
But this is what I was trying. It's only defined on maps from schemes, but that's why I did this little discussion here to extend to sections over any map, étal map of DM stacks.
Could you not also define global sections via an appropriate limit or co-limit in the original category without adding in maps from Deligne Mumford stacks without being able to evaluate?
Yeah, I think you could. Yeah.
Okay, thanks. Wasn't sure if there was some technicality that.
No, I think that's right. I was trying to define it in the most explicit way possible. But right, yeah, for the pre-image, you just take the limit, like the limit over all sections where V contains the image of U. Right, and then, so as an example of a sheaf, we have the structure sheaf.
Sorry, can I ask one thing? Mm-hmm. In the map from U to V, you wrote étal. Are you saying that map have to be étal just at the bottom in your little diagram? So like U is étal over X and V is étal over Y, but is it clear that I'm just.
I guess this map doesn't need to be étal. Yeah.
Okay. Thank you. Sorry.
No, you're right, because otherwise that would have applied X to Y as étal.
Exactly. Yeah. Okay. Thank you.
Right. So as an example of a sheaf, we have the structure sheaf, and so we'll denote it O of X, and for an étale morphism from a scheme U, we just take the global sections of U. And now we have a sheaf of rings on this site. We can define OX modules just like with schemes. And we have a similar adjoint functors. We can push forward and pull back OX modules along maps of DM stacks. And so here I've just sort of saved time by writing it out. This just denotes the category of OY modules. And the pullback is done like with schemes where you tensor with the structure sheaf to make it an OX module. Right, so now we have OX modules, and then the one additional thing we need is quasi-coherent sheaves. So we say an OX module F is quasi-coherent if its restriction to any étale cover is quasi-coherent. If for all maps from a scheme, the restriction, I'll write it as F to U, but to the Zariski topology of U, to this is the Zariski, the small Zariski topology of U, is quasi-coherent on U. It's a quasi-coherent OU module. And the point is that, yeah, I mean, to get a Zariski sheaf on U, for any open set in U, sort of the composition then to X is still étale, so we still have sections over that. So you just only remember those sections, and then you get a sheaf in the Zariski topology of U, and we're requiring, and you also get an OU module, and we're requiring that OU module is quasi-coherent. And we have the same sort of functors between the push forward. So the fact is that so this is, let's take a morphism of DM stacks. One is that you can pull back, and this preserves quasi-coherence. And the same thing with the push forward with a weak separation condition. If it's quasi-compact and quasi-separated, then the push forward also preserves quasi-coherence. Great. Any questions on the definitions? Oh, these facts take work. I'm not, just because I have limited time, I'm not going to do this. I want to get to MG, but yeah, they take work, but it's manageable.
So the definition of quasi-coherent, is it enough to check it once for an étale presentation?
For a single étale presentation, have to think about that. It's a good question. I mean, you could, I'm not sure actually. You can, I'll say a few words later about how you can define them. And like in the moduli context, maybe in the groupoid context, if you have a given presentation and then you take the corresponding groupoid, you could define, maybe this is the answer to your question. Then you could define a quasi-coherent sheaf. So maybe, so if we have, okay, in the bottom left, if we have X and you choose an étale presentation, and then you take the corresponding groupoid, and you only wanted to define it in terms of this data, you would define it just like you would do with descents. You would say it's a quasi-coherent sheaf on F, but you would need an isomorphism over the pullbacks to R that satisfy a co-cycle condition. So I don't think you can get away with just saying that. I guess I still don't know the answer to your question. But.
I think when, like for BG, if it's just a module, it'll definitely pull back to a vector space on the natural cover. And that would suggest that all modules are quasi-coherent over BG, which seems not true. I don't really know.
Yeah, a good point. Yeah, let me avoid this. Let's save this for the discussion period.
Okay.
I do want to talk, like Gabe just brought up a good example, which is BG. So let's talk about quasi-coherent sheaves on BG. Let's take G to be finite. Then the category of quasi-coherent sheaves on BG is equal to the category of representations of G. Algebraic, or linear representations. And you can see this, either by taking sort of the groupoid presentation of BG, which is spec K over BG, and then you have this groupoid, which is just G. And so if you pull up, the descent condition corresponds to an action of G on the vector space. And so let's take a vector space V and try to understand, and let's consider what these natural maps. So I have over BG. So I have sort of this diagram. Let's call this map P. This is our Étale presentation. And then we just have the structure map to spec K. And the first thing you can do, so let's take V to be a G representation. If I pull it back along P, this is just equal to V as a vector space. You forget the G action. On the other hand, if I push it forward, I recover the invariance. You could also ask what happens if let's suppose I have a vector space W over K. If I pull that back via pi, this is just W as a trivial G representation. Or you can also think about W on spec K and what happens if you push it forward. Well, what you get then, it's the same thing as taking W as a vector space and tensoring it with the push forward of just the one-dimensional representation. And this here is the regular representation, which is just, you can think of as the global functions on G. Right, so you say, but this is, sort of an important point that quasi-coherent sheaves on BG correspond to representations, and therefore quasi-coherent sheaves on like a moduli stack corresponds to like a family of representations under the stabilizer groups. Great. So I just defined quasi-coherence. Wait. Yeah, this. Makes me think I forgot to say something. All right, so where are we? I want to give just maybe another perspective of how to view quasi-coherent sheaves. So if you have F quasi-coherent sheaf on a Deligne Mumford stack, then by definition you have by definition you have quasi-coherent sheaves on all the pullbacks under Étale maps. But you can even extend this to not just Étale maps, but all maps. So you actually get the data for all maps S to X, where this is a scheme, and this is not necessarily Étale. You get a quasi-coherent sheaf. Well, let's write it Fs on S, with the property that if you have a morphism S to T of schemes, over X, that you have a canonical isomorphism between the pullback of Ft to Fs. And this is sort of a useful perspective in the context of moduli problems, because, for instance, like let's define a nice quasi-coherent sheaf on Mg. So I'm going to define a sheaf H. This is going to be the Hodge bundle. It's quasi-coherent sheaf on MG, where what I need to do is just for every morphism, say S to MG, I need to define a quasi-coherent sheaf on S. But yeah, this map corresponds by definition to a family of smooth curves. And I define, so H, S, I could take the push forward of the relative canonical sheaf. And because of properties of the canonical sheaf, like if I push forward and pull back, it's the same as pull back and push forward. So you get these canonical isomorphisms, and therefore it defines a quasi-coherent sheaf. All right, and this is called the Hodge bundle. But there's a lot of other constructions you could do. You know, you could take the determinant of this thing, or you could have inserted, you could have taken powers inside here. And it's a very useful way, like in moduli problems, using the geometry of what you're parameterizing to cook up natural sheaves, and then you use them maybe to, for instance, what we'll do is we'll use that to get line bundles on our moduli space, and then try to verify that they're ample. But now once you have quasi-coherent sheaves, there's a whole other like sequence of notions you can introduce. And I'm not going to spell them out here, but you can define vector bundles, right? This should be, these should be locally free quasi-coherent sheaves of finite rank. And then inside here, you have line bundles. You can discuss coherent sheaves, at least with X, like say X Noetherian. You can discuss OX algebras, A, and then you can use this to define the relative spectrum. Like given an OX algebra properly defined, you have this sheafy spec of A over X, which is an affine morphism. Oh, I disappeared. Right, all right. Any questions on this? I think that basically sums up, yeah, this is my quick recap of quasi-coherence.
When you say that isomorphism is canonical, do you mean natural?
I mean, whatever you want. Yeah, no, that's a good question. I think I'm gonna, yeah. What do you mean by natural? Yeah, let's say natural.
Natural means that there's a commuting square. Like if I have a...
Yeah, that's what we want, right? That, like, I think that, right, if you wanted to spell out what, like if you had a composition of morphisms, say S to T to U, you'd want these to pull back naturally, yeah.
So this isomorph is the part of the data of quasi-coherent sheaf in this description?
Well, but that's not how I've defined it, but I'm saying this is, yeah, this would be an equivalent perspective. You could give an equivalent definition like that.
Okay, I see.
And how do you define stalks of such modules? Does it even make sense?
No, it's a good question. We're not really. I mean, we're not. You always argue in terms of a presentation, and then you can take stalks. But
okay. So only when you present the stack, and then okay.
Yeah, but on the other hand, like part of the reason I wanted to introduce the residual gerb, I keep talking about the classifying stack of stabilizers, is because this is like the right analog of the, of the fiber of a quasi-coherent sheaf is the restriction to the residual gerb, not maybe to a field value point. Like the fibers of sheaves on schemes, you always restrict to the residue fields of points. Here, right. If you do that here, you lose information. Like the difference between from going, like if you have...
because it doesn't remember the stabilizer structure.
Exactly, it doesn't remember the stabilizer. So here's your PG, which is sometimes the residual gerb. and you have a quasi-coherent sheaf. If you pull back all the way to spec K, you lose how the stabilizer group is acting.
All right, yeah, that makes sense. Oh, thank you.
No problem. All right. We actually, and so I'm going to turn to the third topic where we won't actually use these quasi-coherent sheets, but we will later in the course. Well, that. Right. So now the third part of this course is local structure of DM stacks. And so yeah, here's the theorem. So I take a separated Deligne Mumford stack. I take a point defined over an algebraically closed field. So yeah, that's what I mean by geometric point. I mean, K is K bar. And I have a stabilizer group, GX. And this point, because I'm taking K equals K bar, the stabilizer group is an honest, finite group. It's not like, say Z mod 3 over spec R, where it's just a form of Z mod 3. Or, sorry, mu 3, yeah, over spec R. So it's honest finite group. And then the conclusion is that a tau locally around this point, it's isomorphic to a quotient stack by the stabilizer. So this gives you in a tau cover, tau and affine. And moreover, you have this sort of important property that F induces an isomorphism of the stabilizer groups at W. So here, W is sort of a choice of a preimage. So I have spec A. And then this is my quotient stack, W. And this maps then to X. And so this is my point X. And I could even have W to be a point of this, of the spec A. And the condition is then that, when I mean isomorphism of stabilizer groups, is that it's an induced map from that the automorphism group, in this category W of K of W maps isomorphically to the automorphism group in X of X. Actually, and what this actually implies is that the GX action on spec A fixes this W as a K value point of spec A. Oh, that was, yeah. And right, so this theorem is really important because it tells you that locally your stacks are quotient stacks. So really the upshot from more of like a philosophical perspective is this tells us that we can view DM stacks as these nice quotients of affine schemes by finite groups as the glue to tau locally. And I'm guessing some of you are thinking, wait, didn't we define Deligne Mumford stacks as just gluing schemes together tau locally? How is this any different? And it's different because that we're getting that our tau covers are actually preserving the stabilizer groups. So they're preserving, so they're it's sort of an analog of like a Nisnevich tau covering. Nisnevich tau covering is one that you can arrange that there's always a preimage that induces an isomorphism on residue fields. Here, you can arrange, here this might not induce an isomorphism. This might allow residue field extensions, but it at least induces sort of an isomorphism on the stabilizer groups. So it is almost inducing an isomorphism on residual gerbs. You could do better than this if you want, but this will suffice for us. Right, all right, so my goal in the remaining 20 minutes, actually, I don't think I'll need all that time, is to prove this. So here's some, I'm going to get started with the proof. I'm just going to introduce some notation. And that, so we're going to choose an Ital presentation to start. So let's let this be an Ital presentation where U is a scheme. And we're going to take use of these fiber products. So I'm going to take the d-fold fiber product. And observe that a map from S, so what this stack classifies is that a map from U to X to D. Well, if you think about what that is, it's a bunch of objects of U that become, and then isomorphisms in X. So I might as well just fix an object in X. So this is the same data as an object S in X. And if I consider the corresponding fiber product, so this is maybe X, I also have D sections. So S1 to SD. And I'm going to set U mod X D0 to be the open substack, which is the complement of all diagonals. So in other words, if I just repeat this notion here, and I map instead into this open set, then I'm getting disjoint sections. Yeah. And the final piece is, what we also have is we have SD actions. SD acts on both this locus and it's an invariant locus inside here, which just permuting the sections. So this will be our construction. Right, so let's now prove it precisely. So the way we start, whoops. So let's choose a particularly nice presentation. Let's choose U over X, a tau. And let's choose this to be an affine scheme. And I can arrange that if I take the pre-image here, that is just 1 point. I know it's a tau. I don't need to do any slicing argument here. I could just throw away all of the all of the points in the fiber other than one particular point. And moreover, I sort of had this assumption here that X, was separated. That implies that the diagonal is affine. And so if U is an affine scheme, that means that this map is even an affine morphism. Yeah. The separatedness assumption is not necessary for this proof. I mean, it goes through fine with if you have any DM stack, as long as I think you need to know that diagonal is quasi-affine, but that's true. Although that fact we haven't shown. But anyway, I'm restricting to separated DM stacks here. And so now let's let D be the cardinality of this finite group being the stabilizer group. And so this map here is finite étal of degree D. And in fact, if I base change one more time, right, what I get is the stabilizer. All right, and then I had these constructions. I had U over X to the D, right? This is just this fiber product. And I know this is an affine scheme. because U is affine and the morphism to X is affine. So I actually get an affine scheme. And that implies that I'm going to define this as W as the open substack parameterizing disjoint sections. And then this is quasi-affine. And remember here that, actually, maybe I could, yeah. That we had that we knew what objects of this were. Right, objects of this were disjoint sections. Oh, of the open, yeah. So this is W. And for instance, so if I have such an object here, you know, I can construct, like, given S to UX D0, if I just, these are disjoint sections. So if I just consider sort of the disjoint union of all of the images of at these sections Si over U, I get a closed subscheme of US over U. Oh, sorry, that's S. And the point is that this map is finite étale and of degree D. In fact, it's the trivial finite étale cover of degree D. And right, I have an SD action. SD acts on UX D0, and I could take the quotient. Oh, this was W, yeah. I could take the quotient W mod SD. And what this classifies then, this stack classifies like a map from S into W mod SD is the stackification of like forgetting, is this like sort of the stackification of such objects. So I'm gonna get finite étale covers that are not necessarily trivial. So this corresponds to Z inside US over S, where this map is finite étale and degree D. And so for instance, I have an object. So I can define W. I have an object over the stack W mod SD by just thinking about what happens if, I have the following object. I have U over X. I have the K point I begin with, X, and I know this fiber product. I arrange this fiber product to be GX. And I take Z to be equal to GX as my closed subscheme. And a choice of ordering, maybe I'll go on to the next page, where, let me just, copy this part, or maybe this part. Right, we have this and we have this point here, and what I want to say now is like a choice of ordering, of ordering elements in the stabilizer gives a lift W tilde actually to the scheme W, to this quasi-affine scheme W. And here, maybe I'll just I'll argue that you could check this fact, that under the SD action, the stabilizer of W tilde under the SD action is precisely the stabilizer, GX, inside SD, right? where this is the stabilizer naturally embeds into SD, because D is the number of elements, right? This is like the regular, one of the standard representations, right? And just the stabilizer moves around those elements, and that gives me this inclusion. Right, so we have our picture. Just to maybe recap where we are and what we know is that I started with X. I took a nice presentation, and then I constructed this stack over here that has an SD action. Oh, that was, yeah. And then inside here, I have SDX. And then this was my W. I then take my quotient, mod SD. And this maps to X. And basically, yeah, this is our presentation. We're basically done. This is maybe you also need to check. This is our map F. Check F is representable. Well, that one that is defined too, that it's representable. And a tau. But actually, it's a tau because everything in this diagram is a tau. So it's yeah, the talness is easy. And the representability, you just need some patience to sit down and check it. But we also know, and this fact implies the F induces an ISO at on stabilizers. At W. So I think we're basically there. What else is remaining? Well, there's a couple things actually, right? Where there's, well, right now we've basically arranged everything in this theorem except for, well, I guess 3 things. One is that we have W, which is quasi-affine, not affine. 2 is that we have an action of SD rather than the stabilizer. And 3 is we haven't shown that the map is affine. So let me quickly sort of sketch that. Let me just, yeah. First is that, so maybe for the first issue here, is that we can just consider instead the stabilizer, this composition. The stabilizer lives inside SD, so I can just forget about SD. And this has this composition is a tau, and also preserves the stabilizer at W. Okay, and but we also know, so maybe to handle the affineness, we also know that W is a fixed point inside this quasi-affine scheme. Is fixed by the stabilizer. So therefore, if I just choose any affine open, that choose W inside W with affine open, containing this point W, and then I could take the intersection under the translates of this. We call this W double prime. W is still in here, still affine, and now it's G invariant. So this is our spec A. Right, and the last thing I owe you is 3. Why is it affine? And here we're going to use our assumption that the stack was has affine diagonal. So what we have, so we now have spec A mod the stabilizer mapping to the stack, and we know it's representable. And I want to argue it's affine, but I also know that after a finite cover, this is so after a finite surjective, even a tau cover, I know this composition is affine because X has affine diagonal. And this will be enough if you can argue via descent, for instance. Let's just choose like U affine over here, choose this a tau presentation, pull this back. I'll just write this as U prime, U double prime. And then this is still a finite map. U double prime is affine, U is affine. And then we use Serre's criterion tells us that affineness descends under finite morphisms. Just, yeah, it tells us therefore that U prime is affine, which in turn tells us that spec A mod GX to X is affine. And I think that wraps up the proof. I'll end the recording now and then we'll have questions.